chapter 10.4, Green's theorem in a plane. Okay? So far, you've learned the line integral. This one, this character. This is closed integral. Okay? It's an integral along the closed curve. That's what it is. Okay? So this theorem is very powerful in the sense that it states the relationship between line integral and double integral. Okay? So you learned, so far the line integral, and you reviewed the double integral, and you can, switch between those two freely on your own. Okay? So if the problem is given to calculate on double integral, but it's hard for you to calculate it really, then you can switch to line integral and get the answer. Okay? That should be the same. If the problem is given in line integral and you feel like having trouble parameterizing that curve, then you can do double integral. Okay? So that's very powerful theorem, Green's theorem. This is really powerful. So you're switching between two double integral and just one integral, line integral. Okay? Right. But not all the integrations can be done in this way. But we have some conditions to do that. Right? We have some conditions on the curve C. Okay? So not that. So x, y plane, let's say we have certain region R, okay? And that's a region that we wanna integrate over, right? Then this region is bounded by some curve C. That's the situation. Okay? So that's the situation. Then we have some conditions on those. First one, simply connected. The C has to be simply connected like this. Okay? It starts from a certain point and then it ends at a certain point. Okay? That's simply connected. So this is not simply connected. Okay? If you have a crossover, that doesn't simply connected. But no matter how complicated the curve is, as long as it doesn't cross, that's fine. That's simply connected. Okay? All right? And second condition is it has to be piecewise smooth. So it has to be a smooth function, but piecewise. All right? So like this, that's fine. Okay? That's fine. As long as this piece is smooth, this piece is smooth, and that piece is smooth, that's fine. Okay? All right. And it has to be counterclockwise. That's positive sense. Okay? If it's a positive, that has to be counterclockwise rotation. So that has to be, like that. To use Green's theorem. Okay? And one last, special condition is, if you have an inner hole, it's a hole, okay? In the region, inside the region, if there's a hole, the boundary curves that's surrounding C, the hole, this is the boundary curve that's surrounding the hole, that has to have opposite direction. Okay, the outer boundary has counterclockwise direction, that's positive sense, then this has to be clockwise, opposite direction. Okay? That's 4 conditions. If that conditions are met, those conditions are met, then you can use Green's theorem. Okay? In vectorial form, that's what it is. So, this is dot product, dot, and this closed curve. Okay? And see, this is curve. Why? Because df2 over dx, right? That's df2 over dx minus df1 over dy. That is actually curve f dot k. because curl is I, j, k, d, dy, dz, f1, f2, f3, and dot with k. Okay? Dot with k means, you know, this one vanishes, this term vanishes, right? And you have only these two terms left. Okay? That's what you get. This is a part of a full proof. Okay? This is not proof of everything. This is just a part. Okay? On the textbook, it says we have this and we have that kind of region, right? And we have x perspective, that's a to b, that's u of x, v of x. That's the upper bound, okay? The upper bound is v of x, and the lower bound is u of x. Okay? This is x perspective, okay? And on y perspective, same thing, but on y perspective, so it has to look like that, and but y perspective, so it's c, d, and that one is I think it's q of y, and that's p of y. Okay? So we have this double integral in this situation. That's the same r. Okay. And we're gonna, you know, prove that the double integral df2 over dy minus df1 over dx dy. Am I right? I'm sorry. df2, that's x and that's y, right? And the line integral of f1 dx plus f2 dy. Okay, that's the integral, and we are proving it. All right, so let's prove this term first. Okay, so r df1 over dy dx dy. Okay, so we're gonna, you know, calculate each one by one to see if it's true. Okay, and that is from this is x perspective. Let's assume that. Then that's u of x, v of x, df1 over dy, dx. Okay, if it's x perspective. Okay, and then that's what the inner side. The inner side is a to b. The inner side is f1 of x comma v of x minus f1 1 of x comma u of x dx. Okay, the inner one, this one is actually, you can write that way, right? All right, then this one is what? So this, you can write this way from okay, so it's b to a to make it minus a to b f1 of x comma u of x dx. This is, I'm sorry, this is dx there. All right? Okay? And to calculate it. And the double, I mean, the next one is Anyway, yeah. So that is actually minus c f1 of x comma y dx. Okay? Is it true? So that's v of x, right? That's v of x, and a to b f of x, right? So it's a full closed integration. That's the line integral, but it's a minus sign there, right? Right? Okay, then now we're gonna do the second one, right? This one, this term, okay, this time, right? So here, r df2 over dx, dx dy. Okay, same procedure. From c to d, p of y to q of y, df2 over dx, dx dy. Okay, and the inner integral from the same stuff. f2 of, it's a q of y because it's x position, right? And y dy plus d to c f2 p of y dy, and that's the full closed loop line integral dy. Okay, and if you add them, these two, that's what it is. So f1 is y squared. It's a vector field, right? And f2 is 2xy plus 2x, and c is a unit circle. Okay? So in that case, we calculate both ways, okay? Double integral and line integral, and we're going to compare the calculation results and see if it's the same, okay? So the first one is double integral. Let's do it. df2 over dx minus df1 over dy, dx dy is what is it? So df2 over dx is 2y minus plus 2, right? Minus df1 over dy, it's 2y minus 7. Okay, that's dx dy, right? And you can, and this cancels 2y, right? And it's 9. So 9, comes out of the integral. So that's it, right? But this one is what? The area of a circle, right? So that's 9 pi. The area of this circle. Okay? And let's calculate the line integral. To do the line integral, you have to parameterize it, right? Okay? So f1 is, so it's x is cosine t, y is sine t. Okay? And you plug it in. And f1 to be what? Sine square t minus 7 sine t. f2 is 2 cosine t sine t plus 2 cosine t. Okay? And so the line integral, f1 times x prime plus f2 y prime dt. Okay? That's a parameterized, calculation, right? Is from 0 to 2 pi, because t is a full circle. It's from 0 to 2 pi, right? And you plug this in, sine square t minus 7, 7 sine t times x prime, which is minus sine t, right? Plus f2 is this here, and times y prime is cosine t, okay, and dt, Okay, I'm not gonna, it's on the textbook, so you try it on, and that's. So we have, same calculation result, and from this, example, we just verified, Green's theorem is okay. That's fine, all right? That works. So this is the problem. dx plus 2xy dy, where the region R is xy coordinate from 0 to 1, and 2x squared, the y is bounded by 2x squared and 2x. So we have to, first draw the region x, y, and x is from 0 to 1, so 0 to 1, and okay, and y sense is bounded by 2x squared and 2x, so we have to, first draw these two functions. So 2x is like this, right? This is 2, and 2x squared, it looks something like that, right? So it is a region bounded by these two functions. Okay? And definitely it has to be in the, counterclockwise sense to be positive. Okay. So let's assume this is a line integral, but let's assume that this parameterization is really, really hard. So we can't do that, okay? Let's assume that, all right? This parameterization is so hard, we cannot do it, okay? Then we feel like, having the double integral, right? Because this function is quite obvious in here, right? It's 2x squared. This function is well defined, right? So double integration will be much easier, we feel like doing it. So from 0 to 1, oops. So 2x squared to 2x, and that's df1, df2 over dx, that's 2y, right? Minus df1 over dy, that's minus 2y, okay? And that's dy dx. So from 0 to 1, that's 4y, so it's 2y squared from 2x squared to 2x and dx. From 0 to 1, 8, so it's you plug this in, so it's 8x squared minus 8x to the 4th, and that dx. So it's to integrate it, 8 over 3x cubed minus 8 over 5 x to the 5th. So from 0 to 1, alright? So 8 over 3 minus 8 over 5 and 0, 0, that's 16 over 15.